Alright, for this next topic, we're finally going to get into stuff that you're going to do in lab frequently. First step is we need to figure out how to calculate the formula mass of a compound. And we're going to talk about moles and what this Avogadro's number means. The formula mass is actually pretty darn straightforward. What you do is you look at the subscript. It says I have 6 carbons. So for carbon, make sure you can see that. For carbon, I'm going to have 6 times, come over to my periodic table, and you want the atomic mass, 12.011. 12.011. Hydrogen, I have 12 of those, times, come over here to the hydrogen, and, oops, make sure you can see that. Too much stuff on my desk right now. Come down here to hydrogen, I have 1.008 atomic mass units, 1.008. And oxygen, I have 6 of. See the 6 subscript there? So 6, now let's go to our periodic table. Look at the atomic. Sorry. Dinner time. Oxygen, I have 15.999. I'm just going to go ahead and round that up to 16. Let's see what these come out to on the calculator. Okay, so when I put it into my calculator, I want to point something out. I did enter in the 15.999, and that's important only because one of the fatal flaws that I see is somebody doing what I just did. You know, there's no reason to write .999. It's just 16. And then you come back here and it's time to do sig fig analysis, and instead of doing 15.123, which is, that's a horrible 9, which is 5 sig figs, I'd come over here and suddenly round down to 2. And when you're in lab, that can be kind of catastrophic to your final answer, so you don't want to do that. For example, it's okay, but when you're learning, I shouldn't do that. So this number is a result of 6 times the 15.999. So 5 sig figs, 1, 2, 3, 4, 5. Whoops, 5, I can't count. This one is 1, 2, 3, 4, 1, 2, 3, 4, can be there, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, there. Now I'm going to add them all together. So sig fig rule, it is the least amount after the decimal, so our final answer is only going to come out to the hundredths. Now let's add them. And I get 180.156. So like I said, because our sig figs get limited here to the hundredths, that means that this answer can only be in the hundredths. What I didn't do is do any rounding before I added them up. So this is a reflection of all of the digits carried through until the final answer. I just went ahead and double checked here. Alright, so what does this mean? This means that the atomic mass units for this particular molecule, the C6H12O6, is 180.156 atomic mass units. So there's a couple options that you can do there. You can say, well, I would like to know what that is in grams, and we could certainly do that conversion. Or we can now introduce this concept of Avogadro's number. That's what this guy is up here. What this means is that I have 6.02 times 10 to the 23 particles per mole of a substance. And the way he came up with that was defining carbon 12. He looked at the 0.01 or 011. He looked at this number and deduced how many carbon atoms had to be in the isotope, the carbon 12 isotope of carbon, and came up with this number. This is just like saying a dozen eggs, or 12 eggs in a dozen, or what are some of the other things we commonly kind of compact down and everybody knows? Yeah, and like the 12 eggs in a dozen is the one that just sticks to my mind. This lets us take these numbers, and instead of going AMU to kilograms, now we can talk about them in terms of grams, because all of these numbers are grams per mole. So if I have grams per mole, I can work myself into any of the values that I'm going to use in lab. That becomes a useful number, and then I don't have to worry about converting between my AMUs, because quite honestly, we're not out just dealing with 6 carbon and 12 hydrogen and 6 oxygen. That would be this teeny tiny system that we wouldn't have the means of dealing with in lab. What we can deal with is 6 moles of carbon, because if we're talking about something that's 72 grams, instead of this teeny tiny 10 to the negative 27, or 10 to the negative, oh, now I've forgotten what the conversion, 10 to the negative 23, I think it is, I'd have to look it up, AMU to kilograms, I have real numbers that I can deal with in the lab. So let's see how that works. So let's think of a different way to think of this then. What that means, what that means is that I have 6 moles, or 6 times 6.02 times 10 to the 23 carbons. I have 12 times 6.02 times 10 to the 23 hydrogen, and 6 times 6.02 times 10 to the 23 oxygen in 1 mole of this molecule. That's a lot. Fortunately, we won't make you think about it too hard, but you do need to know that that's a lot of little parts and pieces that go. And all a mole is defining a unit of essentially 1. 12 eggs in a dozen. And I'm too tired to come up with other examples, but let's move on to using it.